Let me introduce Marco first. So Marco Garcia Porcel holds a PhD in optical sciences at the University of Twente, and his thesis was devoted to photonic integrated circuits and nonlinear processes, and in particular nonlinear generator and acousto-optic control of light in osteochromatic silicon nitride. And since then, he has been working both in academia and now in industry, as he is currently R&D manager at VLC Photonics, where he is involved in managing several Horizon 2020 research projects related to integrated quantum optics. And he will talk us about photonic integrated circuits for quantum signal processing. So I'll lead you the role, Marco, and show us your presentation.
Okay, can you?
I can see the presentation. Yeah, very well. Okay. And we also see the mouse.
Thanks, Alex, for the. Yeah. Okay, perfect. Thanks, Alex, for the introduction, and I want to thank the previous speakers for their introduction to the field in general, and also for the immediate time of introducing some concepts. But my talk is going to be a bit technical on the photonic integrated circuit side, and but I want to start by introducing a bit the company. So this is the outline of my talk. It's first I will introduce the company and what is photonic integration. I will try to go quickly through those slides. Then I will talk a bit about photonic integrated circuits for quantum optics, with special mentions to photonic processors or quantum photonic processors, and to quantum key distribution that Carlos already introduced, but I think it's worth some extra words. And then I will go to the summary and recommendations. So VLC Photonics is a spin-off company founded at from the Photonic University of Valencia, founded in 2011. And we have our office is located still within the campus of the Photonic University of Valencia. We are already about 16 people, 12 of which have extensive academic and industrial experience, and we have a lot of experience in general in the field of integrated optics and photonics, not only on quantum optics. So what we do in the company is we provide all the services for the development of photonic integrated circuits. Basically, it's photonic integrated circuits go from the same as happened with electronics, from having bulk electronics to having integrated circuits, and now from having fiber-based systems or bulk optic systems to have integrated optics or micro optics. And we basically focus on the integrated optics side. This has been driven mainly by datacom and telecom, but in the last 10 years, and
excuse me, Marco. Could you slightly move the microphone a bit apart, because we hear you very, very coupled.
Okay.
Yeah, that's better. Thank you. Yeah.
Okay. Sorry. So this integration was driven mainly by telecom and datacom, but we see a very strong drive for sensing applications, quantum optics, and we'll skip that. Sensing application, quantum optics, biophotonics, and in the case of quantum optics, there are many different applications, not only quantum computers, random number generators, and quantum key distribution, but there are many other applications. But that's we don't develop applications. We clients wants us to develop. So that's our task, and that's the brief introduction to VLC. And I want to now start with the basics of quantum optics, and the principle is the Hollow-Mandel effect, or the Hollow-Mandel experiment that was first reported in the 87. And basically, as you see here, there is a doubling crystal that produces two identical photons that they go through a slit, go through this mirror, and this does the same thing, goes through this mirror, and they find this beam splitter that is exactly the same at exactly the same time and exactly the same place. If these two photons are hitting the mirror at exactly this point, then you have this dip that you see in this graph. So if there is any change in position or any change in time in any of these photons, then this dip that is basically when the two photons go through the two photodetectors, then you will see that that in the moment you go off, then you see all the time that your photodetectors get activated, and if they don't go at the same time, they do not get activated. So these are this is the basics of the Hollow-Mandel effect, and this is also the basics of most photonic integrated circuit processors. So in the case of photonic integrated circuits, we have different applications, and for each of those applications, it's very important that all the photons hold the same transparency range for the sorry, I have some noise here in the room. Give me a second.
I can hear you more or less well, and I'm trying to mutate all other microphones. Can you hear me well?
Okay. Yeah, I think now I can hear you better. I can hear you better. I was having some noise.
Okay.
In the background. So I was saying, from the case of photonic integrated circuits, for this to work, you need that all the photons that you use on your application, they need to be able to travel through the material, and these materials they have a specific transparency range, and for this beam splitter effect to work properly, the best way that has been devised so far is to just use directional coupler that can be tuned to have a perfect 50-50 split. In that way, by just having a waveguide system that guides the two photons to this to each of these inputs, that would be the same as these two inputs for the beam splitter, then they will show the Hollow-Mandel dip in exactly the same way as in the previous slide. The main advantages of peaks for quantum optics are that you don't need to cool down your photonic integrated circuit. It works at room temperature. The only in the opposite side, for example, you have that the single photon detectors cannot be integrated, and they are usually cold to cryogenic temperatures. So at the end, you still need to cool down your detectors, but not as much as when you use a standard electronic quantum computer. So, and another of the advantages that a photonic integrated circuit have is that there is a material technology. So in the moment you go for photonic integrated circuits that are completely available for commercial applications, and you just need to find the right material for the application. That is, there are different materials for photonic integrated circuits, such as silicon, also known as PLC. You have silicon nitride, you have silicon on insulator, you have indium phosphide, you have gallium arsenide. So depending on how you generate your photons and what kind of photons you want to use and how you want to use them, then you need to go for one technology or the other. But all these technologies have been developed for the last 30 years, and nowadays they are reaching a very mature spot where there is a strong drive not only from this field but also from many other fields, and these have become easily scalable and mass produced. And as I mentioned before, there are two main disadvantages. One is that the single photon sources are complex to integrate into a photonic integrated circuit. As Carlos mentioned, it's hard, but there are other ways to achieve this. And the other main disadvantage is that the photon detectors are not yet efficient enough for photonic integrated circuits. And I want to mention two of the applications that have been talked today a lot, and one of them is for cryptography. And in this case, I want to mention that QKD, or quantum key distribution. These are two images from the case of Alice, the transmitter, and Bob, the receiver. These are two images taken from the paper by SECPHO called chip-based quantum key distribution, where they did both transmitter and receiver on chip. And that was published 2 years ago, but the actual work was done a bit earlier than that. And basically, what quantum key distribution does is it generates, using a quantum random number generator, it generates a key. The key is transmitted through through a classical channel and through a quantum channel. So you have your signal that can go through two different ways, through different fibers, and as they reach the receiver, they will go through the same process as the Hubble mantle, but with a much higher control than just a simple beam splitter. That's why you have all these gates here to control the phase and the delay, the coupling, and these are delay lines to control also the pulse-to-pulse signal that you received. And from this, you will be able to detect if in the quantum channel or in the classical channel you had any interference from someone listening to your communications. That's the very basic introduction to what the quantum key distribution, how it works. And this has been realized already in photonic integrated circuits. And in the case of quantum signal processing, it's also very different to the classical the quantum computers, because these are not computers. They don't store the information, they only process it. And you basically introduce different photons that can have different quantum states, and by playing with the combinations of photons and modes that you couple in and the relation between them, then you can make different operations. This is just an example from Tillman, where they by coupling light into these three modes, then they excite they get in the output of the processor a specific output. If they change any of the inputs or they change any of the photons, then they get something different. And these red lines are the experimental measurements, and the blue lines are the expectations and the simulations. And these are just two very simple examples. There are more examples in glass and PLC, in silicon nitride, in silicon insulator, where the people have built similar processors or even much more complex preconfigurable quantum photonic processors like this one, where they program across gate with 8x8 outputs, and they can change the type of gate that they are programming and how it works. And then you have also, for example, boson sampling, that by programming the coupling, you can actually have specific quantum interactions between the photons that you have in. And these are all works already published, and you can just go to check there, because they are really interesting works that have been done. BSC is a member of several consortiums working on quantum integrated circuits. One of them is an Eurostar project funded by the EU, and it's called QPIC, where we are developing a discrete variable quantum key distribution with the University of Geneva, ID Quantique, SECPHO. And this is as one of the applications mentioned before, but as Carlos from QSide mentioned as well, it's a commercial product. We are just working on the integration side. They have already this technology. It's already commercial. You can buy it. And there's another project that within the quantum flagship. It's called CIVIC, also Carlos mentioned, and we are also a member of this on continuous variable quantum key distribution. And these are the members of this consortium. There is another quantum flagship project where we are members, and we are working on the CMOS compatible quantum photonic circuit side. But there are many different partners that they work on 2D materials and on chip nonlinear optical conversion, and on chip on-demand single quantum emitters. And the concept here is to be able to co-integrate these emitters and in a controlled way into a photonic integrated circuit, so it can be used in an optical network. There are other uses for photonic integrated circuits in quantum optics, such as photon sources, photon per generation, or heralded photon sources. But this would be too much for this talk, so I just place some references here for someone that might find it interesting. And with this, I want to conclude with the basic points, the basic takeaways. Within quantum technologies, quantum optics is a critical piece, is a critical technology that can work very well in combination with quantum computers. Quantum optics, bare optics, and fiber-based require extremely accurate fabrication technologies. But the advantage of photonic integrated circuits is that it can help the industrialization of quantum optics to make it scalable, mass-produced, and QSide is an example of this. And the BSC photonics can help to provide support on the development of these photonic integrated circuits for many different applications, and this includes quantum optics. And with this, I would like to thank you for being listening and for your attention, and willing to answer any questions you might have.
So thank you very much, Marco, for your nice talk. Very interesting, and it's a topic that I follow very close as well. I have a question personally. So I don't know if you mentioned it there, or maybe I'm wrong. But I think that also one of the quantum technologies that are being or they will be developed is quantum simulators. So quantum simulators will be like a playground where we could eventually mimic, really simulate a quantum experiment using a quantum device. And as far as I know, also photonic integrated circuits could be used in that direction. Do you know any of the current developments in that field, or if you know if VLC have participated into this kind of initiative?
Okay, with this, I will thanks for your question. I will go through this. So these quantum processors are a way to make these simulations by having specific inputs and specific ways to program these networks. You will have your output, and all the interactions happening in this network is quantum based. So, if you are able to program properly your inputs and your network, you will be able to simulate these outputs and these quantum problems. Is that
Okay.
what you meant?
Yeah, exactly. This is what I mean, because it seems like a very reliable platform for quantum simulation as well, and I think that could be very, very interesting. And I have a second question that is, so we had here like two different types of talks today, so more academic and more industrial, like yours or the one from Carlos from QSide. The quantum technologies field in Spain is starting to move forward since a few years ago, let's say since less than 10 years ago. What partners do you think you would require to implement or to, let's say, bring a whole device from the photonic integrated circuit that you do? For instance, I see that you and QSide, PLC and QSide are very related and can go both into the same line. But are there any other partners that you would require in Spain, and you need to look for collaborations in outside?
Well, a very easy way to answer your question is to look at the civic consumption, where we have SECPHO, we have the Polytechnic, the University of well, several universities, not only in Spain but mainly outside. We have SMEs and institutions for profit like Fraunhofer, and we have telecom integrators and telecom operators. So at the end, if you want to have, for example, a continuous variable quantum key distribution system that can be integrated into a large network like intercontinental or from data center to data center, then you need not only someone that can make your photonic integrated circuit, but also someone that can integrate it into a package, someone that can integrate this package into a system, and this system into a complete module that then the telecom integrators can use and sell to telecom operators. And this also needs to come with the technologies that would make this big work. In the case, for example, of the random number generator from QSide, it doesn't need to be cold, but if you are using different types of quantum key distribution system, maybe you want to use cryogenically cooled down, or at least super cold nanowires or photodetectors. And these technologies, they need to be developed and they need to be integrated into these modules. And for this construction is an example. You need partners, not only from Spain, but also from other countries, because sometimes you don't find this specific knowledge and experience locally, and then you have to go to other partners.
I see, but we can affirm that Spain is well positioned in the field of quantum technologies. At least this is what I can see from this very nice sketch from you. Very good. Thank you very much for your talk. I think it's time to